And in Swinburne's test, we have seen there are two stages. Swinburne's test is a no-load test on DC shunt motor. Okay. Since it is no-load test, I cannot operate this on DC series motor. Okay, this can be used. This method of testing can be used only for shunt and compound motors. Okay. So here there are two stages of testing. In first stage, we will determine the hot resistance. Okay, some around 40 degree above the ambient temperature of the motor operation. And in the second stage, and in finding the hot resistance, what we will do is we will find the cold resistance first. Then we will use a factor of 1.2 multiply it with cold value. Then we will get the hot resistance at 40 degree above the ambient temperature. But practically what we do is we will run the motor, we will dry run the motor. Dry run means at no load. Okay. Most of the times in our houses, when we have uh, these water pumps, okay, you might have heard talking from your parents that if there is no water, if you dry run the motor will burn. Actually, motor will be at very relaxed condition when you dry run it, because there is no load, so it won't carry any current, so it is very relaxed. So when there is no water, winding will not burn, but there will be a problem occurring in the pipes and block. Water will not be entering the winding part in the motor. Don't think that. There is a separate block attached where there is a vacuum created when it starts rotating. And because of that vacuum suction mechanism, the water will be lifted from the sump to the overhead tank. So if you dry run the motor, nothing will happen to the motor, first of all, because motor is on no load. If you run even for 1 hour, nothing will happen to the motor. But what will happen is, with a dry run, the block will get more air filled. The pressure, air pressure will be more in the pipes and the block. So next time when you want to lift the water from sump to overhead tank, you should clear that air pressure in between, or else the water will not be flowing from the sump to the overhead tank, and this will create a blocked rotor condition. Okay, this will create a blocked rotor condition. The motor will refuse to start after some time. If the air pressure is very tight, the motor will refuse to start. Okay. So this is just an information, an additional information, as we have, all of us, we have motors in our house. Okay. How this I got to know is, we had a very old pump in our previous house where we stayed as tenants. So that old quarter HP pump was insufficient to drag the water. So after some time, whenever the water was completely lifted to the overhead tank, the remaining water used to come down. This should not happen actually. The excess water used to come down, and there used to be created a small amount of air pressure between the overhead tank and the sump. And many times this motor refused to start. Okay, when I diagnosed it and I opened the block part, there I observed that there is a large air pressure, and when it was slightly loosened, a large amount of pressurized water what we split it out, and the pressure was clear. So this used to happen every 1.5 months. So I used to clear that. Okay, for the same reason, my another tenant who used to stay in the um, first floor of the same building, he paid twice 500 rupees to the electrician just to clear that air pressure. So if we know certain practical aspects, lot of minimum repair works we can do as electrical engineers in our house without costing much. Only material cost will occur. Okay, or else huge amount of money has to be given for very small amount of work done. You know how much they will charge for fixing a fan? Last time when I asked to fix a fan around 10 years back, it was 250 rupees just to fix the fan. They will unbox the fan and they will fix it. If you really see the connections and fitting, there is nothing in that. And now they may take 400 to 450 rupees. Okay. So small amount of this works, household works can be done, electrical works can be done if you just observe how the things are operating surrounding us. So that will help us a lot in saving the money, as well as we will know if anybody will start to overcharge us if there is some maintenance work. Okay. So that is a hint, okay, a practical hint. Yeah, coming back to the no load test of the DC shunt motor, this all came because of no load condition. Okay. Uh, then in the no load test to get the hot resistance practically, we dry run the motor for some amount of time, for extended amount of time after the test is done. Then immediately by stopping and disconnecting the motor, we whatever the value of resistance I get, that is to be taken as hot resistance. Okay, though it may not be exactly accurate, but it can be considered rather compared to the cold resistance value. So always remember, when you conduct a Swinburne's test, the resistance value should be taken after 5 to 10 minutes of after at least 5 minutes of your test. Don't stop the motor immediately and take RA. This care has to be taken. Okay. Now in the second stage, we calculate constant losses. Since the motor is on no load, okay. So how we run the motor is, first we start the motor. It will be ensure that the motor is on no load. Okay. When we start the motor, check the speed. If the speed is below the rated value, vary the field rheostat and adjust the speed to rated value. Okay. Then note down the readings of voltmeter, ammeter, all the ammeters and all the voltmeters connected. There is no harm. You can connect one more ammeter in armature also. Okay. I can connect one more ammeter in armature. There is no problem. There is no compulsion that there should be only two this ammeters. Theoretical circuit, we don't add ammeters in showing. Losses, iron losses, and friction losses. Okay. So whatever the no load input is given to the is to overcome the losses.
Excuse me, sir. Your voice is not audible, sir.
Now, am I audible?
Yes, sir.
So no load input. is completely utilized by the motor to overcome the no load losses. So I can write no load input is equals to no load losses. No load input is equals to no load losses. Now we should know what are the no load losses. Okay. Now observe, there is a line current drawn by the motor. It is I naught. I naught is flowing through armature resistance. So there are armature copper losses. Field current is flowing through field winding. So there are field copper losses. There is a applied voltage which is creating a flux in the field winding. Therefore, there are iron losses. As the motor is rotating, there are mechanical losses. That is friction and windage loss. So there are four losses which are existing in the motor. We right now neglect the brush contact loss, okay, and the interpole winding loss because IA is very small. Armature current is very small. So therefore, brush contact loss and the interpole and compensating winding loss, we time being will neglect them. Okay. So here at no load, just a minute. Sometimes I have to restart the presentation slideshow. Okay. So at no load, the power drawn by motor is completely used to satisfy following losses. Is completely used to satisfy following losses. Okay, so the first loss is no load armature copper loss. So here I should be writing exclusively no load armature copper loss because armature current at full load condition is again different. Okay, so no load armature copper loss, which is IA naught square RA. And RA is hot resistance here. Okay, you should remember that. IA naught square RA. Then second, shunt field copper loss. This can be written as ISH square RA. Sorry, ISH square RSH. This RSH is not included with rheostatic value. Okay, rheostat is external to the field winding, or I can write it as simply V into ISH. So both will give us the field copper losses. Okay. Then third one, iron losses in the core. Iron loss in core. Okay, that is hysteresis and eddy current loss in all the parts of the core, stator, rotor, in all the cores. Then fourth, friction and windage loss. Combined, these will form mechanical loss, friction and windage loss. Okay, so these are the four losses that the motor input, whatever is taken at the no load condition, is satisfied. Okay, so all the uh, power taken by the motor at no load condition is utilized to satisfy these four losses. Okay, so no load input is equals to, I can say, loss. Okay, but out of these losses, okay, out of these losses, whatever we see, uh, some of the losses remain constant, some of the losses vary. Okay, so when you observe the circuit diagram, armature copper loss is because of armature current. So no load armature current is IA naught. So which is same until the condition of the motor is at no load. But once the motor starts getting loaded, my armature currents are different. So therefore, we already have stated that armature current, armature copper losses are variable losses. Okay, so these are variable losses. These are variable loss. Then shunt field copper loss. We usually operate the motor at constant voltage. Therefore, the voltage appearing across shunt field is always constant. Once the motor is taken to rated speed, then further I need not to vary the field rheostat. Therefore, the voltage appearing across field winding is same. It will remain constant. And hence, the current flowing through field winding is nothing but my VSH by RSH. So my ISH will remain same. Okay. If I have used this RHF resistance, so this is RHF. Then the current ISH is given by V divided by RHF plus RSH. That will remain constant throughout the operation because further I don't use the speed control or speed variation, therefore it will remain constant. So when ISH is remaining constant, copper losses in the field will also remain constant. So therefore, shunt field copper loss will form a part of constant loss. Okay. And iron loss, we already have analyzed that iron loss in the entire motor will remain practically constant as long as I operate it with constant voltage and flux density. So flux density, there is no question of changing flux density. Therefore, my iron losses will remain constant. And as I am operating the voltage at constant voltage, therefore my iron losses will remain constant. So hence iron losses will form constant loss. So once the motor starts rotating, the friction and windage losses will practically remain constant as the speed is remaining constant. If the speed varies, friction and windage loss will vary. But as I am keeping the speed at rated value at no load condition, my friction and windage loss will remain constant. And as practically the DC motor, especially shunt and compound, are almost a constant speed motors. Hence, my friction and windage losses will not vary much and they practically will remain constant and they will form a part of constant loss. So these will form the part of constant loss. Okay. So now it is clear. If I want to find the constant loss, what should I do? So no load input is equals to what I can write? No load input is equals to no load armature copper loss. I will write the numbers, okay, to save the time. Then shunt field copper loss plus iron loss. All the input is utilized to overcome these only losses plus mechanical loss, friction and windage loss. Now, if I want constant losses of the motor, which will remain constant irrespective of the load condition, what should I do? Yes. Anybody? Am I audible?
Yes, sir.
Then please make yourself audible with the answers. What should I do to get the constant losses?
Input minus copper loss.
Yes. Okay. Not, yeah, we can say that. If I deduct the no load copper losses from the no load input, do I get constant loss?
Yes, sir.
Constant loss is 2 plus 3 plus 4. Shunt field copper loss plus iron loss plus friction and windage loss. So if I simply deduct Ia naught square Ra from the no load input, okay, so I will get my constant losses. Okay, so therefore constant losses are given as, okay, so these three will remain constant. These are constant losses. Okay, therefore I can write constant loss WC is equals to therefore constant loss WC is equals to, I can write no load input or is equals to, first I will write shunt field copper loss plus iron loss plus friction and voltage loss. Okay, so and to get this constant loss, I can write, therefore constant loss is equals to WC is equals to uh, no load input minus no load copper loss. Minus no load copper loss. So I can write a WC is equals to, so what is no load input? No load input is V into I naught minus no load copper loss is I naught square Ra. Or I can write this as, and one thing you should remember here, whenever I am finding copper loss, sorry, constant loss, the DC machine is always considered to be as motor. So this I naught square Ra, it should be always I naught minus ISH square R, Ra. Always. Even when you calculate the constant loss for generator, okay, my equation for constant loss should be this only. Because while finding constant loss, I am making even the DC generator operate as motor. So the Swinburne's test is done, okay, on a DC machine, making it run as DC motor. So you should keep it in mind. So even for generator, while calculating constant losses, my IA naught should be I naught minus ISH only. So once I know the constant losses, okay, once I know the constant losses, I can get the efficiency very easily. The only thing is that now I have to add the copper losses to these constant losses at various load conditions. Okay, if I know what are the load copper losses at various load conditions, then adding copper losses to this constant loss, okay. Uh, so what we are doing here, to get the constant loss, we are deducting no load copper loss. When I add loaded copper loss, it will become the complete loss in the motor. And once I know the losses, I will be knowing the input V into I can get the output. Or I will be knowing the output, I can get the input. Once I know the input and output, I can get the efficiency. Okay. So next to okay, calculation of efficiency. Okay. So before we calculate the efficiency of a motor or a generator, first we should know what we are calculating efficiency for, either whether we are calculating efficiency for a motor or whether we are calculating efficiency for a generator. That we should know first. Okay. So first, uh, we will take efficiency of motor. Efficiency as motor, not motor. Efficiency as motor. Okay. I will call it as eta M. M is for motor. So a motor circuit diagram is to be drawn here because I need to know what is IA. I don't know why this is happening. So much of lag is there. Whether it is a device problem or it is my laptop problem, I don't know. So this is supply voltage V. Uh, this is I, the line current, armature current IA at load condition. This is IA now at load condition. Okay. This is ISH. So for motor, we know the line current is drawn from the supply, and part of line current is shunt field current and armature current. So I can write here IA is equals to, this is very important condition, okay, because we need to know IA to get the copper losses at load condition. So IA is equals to, here for motor, it is I minus ISH. Okay, it is I minus ISH. So using this equation for IA, I should be finding. Then what is I? That is important. From where do I get I? I is mentioned on the nameplate of the motor. So I is the rated line current of the motor or generator. It is mentioned, it will be mentioned on the nameplate, that is full load current. Okay. So if I want to find the efficiency of motor at full load, I should consider full load current. Now, if I want to consider the efficiency at half the full load, can I take half the line current? For a motor, if a efficiency has to be calculated at half the full load, can I take half the line current into consideration? Yes?
No, sir.
We can't take, okay? Because at no load, the line current is not zero. I can take the load factor with respect to current directly only in the machines where the no load current becomes exactly zero. The no load line current is zero. So that is there in transformer and generator only. In motors, it is not the case. In motors, some 10 to 20% in DC machines are always drawn when the motor is given on no load, and almost more than 50% is drawn in induction motors. So it doesn't mean that induction motor is running at 60% of full load when it is at no load. That is a very difficult decision to make for a motor. Okay, so if it is mentioned in any literature that half the full load condition for motor is with half the line current, then that is erroneous. Or they might have mentioned it with certain assumptions, considering no load current equal to zero. Maybe like that they might have considered. But it is difficult to find the partial load current theoretically by using load factor, okay, in motors, because as the load changes, losses change. We say theoretically practical this mechanical losses will remain constant, but as the load changes, there is a slight variation in the mechanical losses. Okay, so therefore a direct load factor cannot be multiplied with line current in case of motors. Okay, so we should not make that mistake. Now, so with this, I can find the efficiency of motor. Okay, so I know the input to the motor. I don't know output because motor is at no load. That is very important. Motor is at no load, but I know the input. Okay, so motor input I can write is equals to V into I. Again, where I is the rated line current specified on the nameplate. Okay, next, armature copper loss. I know the input. Once I find the total losses of the motor, predetermined losses of the motor, then I will deduct that losses from the input. I will get output. I will get the efficiency. So armature copper loss is equals to I square Ra. Now, as this is a motor, my Ia is I minus ISH. Next. Constant losses. WC is equals to no load input minus no load armature copper loss. That is V into I naught. And this I naught is obtained from the test results minus I naught square Ra. And even I naught is also obtained from this test results. Ra is hot resistance. And here this will be always equals to V into I naught minus It is always I naught minus ISH square, even for motor as well as generator. Because even if the machine is generator, I'm running it as motor for the test. Therefore, total losses. WM I will call this as motor losses. Okay, so this is equals to uh, armature copper loss plus constant loss. Okay, so this I will write it as WM is equals to IS square RA plus WC. Okay, now what is motor output? Input minus losses. Motor input minus motor losses. So this I can write it as V into I is motor input minus motor losses WM. Okay. So efficiency, motor efficiency eta M is equals to motor output by motor input. Okay. So I can write eta M is equals to, so motor output is VI minus WM divided by motor input is VI. Okay. So what is WM or percentage efficiency of motor is equals to VI minus okay, so VI minus WM is what? IS square RA plus constant loss WC. So once you calculate constant loss, it will be useful for both motor and generator efficiency divided by VI into 100. So this is the efficiency of machine as motor. Efficiency of machine as motor. Now, I have to find efficiency of machine as generator. Efficiency of machine as generator. So this, let me call it as eta G, just for the differentiation to understand. Okay, just to recognize. That's it. Now, a generator will always give the armature current out. So this is shunt field. You ignore these all extra lines, okay? Every time erasing them becomes time consuming. I don't know what has happened. I will try to fix the issue. It is maybe the laptop lag or my digital pad lag, I don't know. This is RA, this is RSH, and this generator is now giving the electrical output. So therefore my armature current direction will be outward, IA, I and ISH. Now the line current I and ISH are the part of armature current IA. Therefore my IA is equals to I plus ISH. Now suppose there is a DC machine, I don't know whether it is a motor or a generator, which can be utilized in as a both machines. Whatever the nameplate current is given, okay, say suppose the nameplate current is given as 9.5 amperes. So 9.5 amperes becomes a input line current if the machine is operated as a motor, and 9.5 amperes becomes output line current if the machine is operated as generator. So I will be always the nameplate current, the rated current mentioned in the nameplate of the motor or the data sheets of the motor. Okay, that is to be taken for calculation. Now, electrically, I don't know what is the input to the generator, but I know what is the output of the generator. And also, one thing, if a DC machine is mentioned with the output power of 10 kilowatts, that is always the output only, whether it is a motor or a generator. Okay, so V into I is always the mentioned output of a generator, mentioned power rating of the DC machine, whether it is to be considered as motor or generator. Okay. Yeah. So I know the output of motor. So I will take motor output. Sorry, not motor output. Generator output is equals to, it is V into I. Yeah. Generator armature copper loss is equals to I square RA. Generator armature copper loss is I square RA. But what is IA here? It is now IA is I plus ISH. So here it is I plus ISH. While calculating constant loss, WC is equals to, it is again V into I naught minus I naught square RA. This is equals to, down here, V into I naught minus, it is still I naught minus ISH square RA. Because when testing this DC generator, I am running it as motor. So this is the point where most of the students make mistake while calculating copper loss for generator. Because it is generator, they will take I naught plus ISH here, which is completely wrong. Even some textbooks have followed this. Some local author textbooks have followed this in some of the examples. So which is incorrect. Okay, so conceptually we should go for the calculations. Okay. So therefore, here it is always I naught minus ISH square while calculating constant loss, because the machine is tested as a motor. So once I get the constant loss, can calculate the efficiency of motor as well as generator. That is the main theme of the test. Yeah, no total loss. So here I will mention it as WG just to recognize it as losses in generator. So it is armature copper loss, same, plus, sorry, constant loss. So WG is equals to, uh, I can write it as I square RA plus WC. It appears very lengthy when we are doing theoretically. When we do the problems, it is the most simplest test, even in the practicals also. Okay. I square RA plus WC. So this is total loss. Then I know losses, I know output, I will get input. So generator input is equals to uh, output, generator output plus losses in generator or total losses. I can write this as V into I plus total losses in generator is I square RA plus constant loss. Okay. Therefore, generator efficiency eta G is equals to generator output divided by generator input. So I can write percentage efficiency eta G is equals to generator output is V into I. Sorry. Yeah, it is V into I. Sorry. It is V into I divided by generator input is V into I plus I square RA plus constant losses WC multiplied by 100. So here I can say by finding the constant losses in generator as well as by running the machine as motor, I can find the efficiency of machine as both motor as well as generator. So advantages of this Swinburne's test is that it is a very simple test because the machine is operated at no load. Therefore, the power required is very much minimum and it is much suitable for large machines. Okay? Because it is operated at no load condition, it is much suitable for larger machines. Okay? And once the constant losses are known, I can find the efficiency of the machine both operating as generator as well as motor. So these are the advantages. The disadvantages are uh, because the machine is rotated at or operated at no load, it will not take the stray losses into account. These are a new type of losses you are listening to, which we will get to know or I will explain in detail when we see the further tests. In further all tests, we calculate stray losses. Okay, so it will not consider stray losses into account. Stray losses will occur only when the machine is loaded. Okay, stray losses will occur only when the machine is loaded. Because stray losses are not considered into account, the temperature rise of the machine is not taken into account. Because the machine is operated at no load, that too for a very short amount of time, the temperature rise study cannot be done using this test. So this is second disadvantage. The third disadvantage is that the armature reaction effect is not observed or not taken into account in the test. Because to happen armature reaction, armature current should armature should develop sufficient amount of armature flux so that it will oppose the main flux or it will react with the main flux. So since the no-load armature current is very less, since the no-load armature current is very low, the armature reaction effect is very much negligible and hence cannot be studied using this test. So these are the three disadvantages, that stray losses are not taken into account or the load losses are not taken into account. Temperature rise is not cannot be known, and the armature reaction cannot be observed or cannot be taken into account. So these are the disadvantages of Swinburne's test. Any doubts so far? Then we'll end the class and you give the attendance.